Right. So basically, when you talk about, if you have any questions, feel free to ask. Feel free to ask and disturb me anytime. Right. Okay. Right. So when it comes to digital machines, based on they have some, we can identify some major steps in any computer system, right? And that you already know, it's input, process, and output. These are the three stages. And the arrowheads represent the flow of data and information, right? We process data and information here. I mean, we input data and instructions here, and we process data into information, and then we output information here. This was the earlier structure way back, right, in the history. This was the structure of the computer, where we had to input data and instructions separately from outside by means of wiring, changing the wiring, and later on by means of other input methods like punch cards, right? You must have heard about punch card system, where they had punched holes in a certain pattern. That was the input to the system. And later on, a scientist called John von Neumann, came up with a model where it could also include something called storage. And we could store data and information now in the storage. Well, when it comes to storage, there are two types, right? We have the primary memory. This you already know, right? You have learned this for IT as well, which we talk about RAM and ROM. Primary memory, main memory, right? This is also called main memory, primary memory, or even just memory. If they mention like this, it refers to the primary memory. And the other type of memory or the storage is called the secondary storage. And this is also, secondary storage, which is the permanent storage. So now the storage came in, and the data and instructions could be stored permanently in secondary storage. At the same time, they could be stored temporarily on RAM before, so that you can keep them before and after processing. And why the arrowhead is heading both ways, we can store and we can restore. We can store and retrieve data and instructions from the storage. Okay, right. So depending on how these computer systems process data, we can come across three models. One is the sequential model. In sequential model, just like the program, just like the program instructions, in here, the instructions are carried out, executed one after the other in an order. One after the other, simple, right? Step by step, just like a sequence control structure in programming. Then the next one is parallel, right? As the name suggests, parallel means instructions are carried out at the same time in two different places or two or more different places. So the best example that you can take for this is the cores, right? You all know what cores are, right? Right, cores are small processors built into one unit as the CPU. And nowadays processors, they have multi cores. So this is core 1, right? This is core 2, core 3, core 4. Now having a small process like this enables the processor to carry out multiple instructions at the same time. While this do one instruction, this will do another instruction, because these are physical cores. We are talking about physical small process built into one unit. We also have logical cores, but when you have multiple brains, we'll be able to execute many instructions at the same time in parallel. Okay, so we can take CORS as an example for this parallel model. And here, the computer processes, they mention a term called processes, right? Now, this process is a program or a part of a program which is in running state. When a program is running, we call it a process, and multiple processes are called processes. Okay, that's what processes means here. What happens is these processes are distributed among 2 or more processors. Now, these processes are referring to cores, small processes built into one unit. So they are spread across multiple cores. It's just like when your teacher asks you to do a work, you divide the work among your friends in a group. So your friends in a group are like cores, and now the efficiency is high rather than doing that same task by one person. Right? Each separate part of the algorithm that each processor processes can be combined together. Right? These are processed in different cores, and then the results are combined, merged to produce the final output. Okay, something like this. If we are inputting 2 numbers and outputting the average, the input part can be done by the first core, and the totaling can be, distributed to core 2, depending on the availability of these cores. And the average may be output by the core 3, right? That's how it happens. So it's far more efficient than having a single core processor, right? It also requires software programs capable of distributing. Now, there should be someone to distribute the work among these cores, and that is done by software programs, system software, right? Okay, and the next model is called multi-agent. Yeah. Go ahead.
I have a question, sir.
Yeah.
So, so now when we speak about cores split the job, no, sir, like split tasks, no. Now, in this case, is it applicable to take a core in even now? Let's say adding. Now, let's say for a calculation, one is for multiplication, one is for adding.
Yeah.
So, is it practical that all, let's say 8 cores are there, all 8 cores are used for different signs, or is it practical that they use it for bigger tasks?
No, it's like this. Now you can't exactly tell. You can exactly tell that okay, one will take the addition, one will take the multiplication, like that, right? We had to take it as a process, right? When now I just took addition of 2 numbers as an example, right? But actually, right, in reality, these are processes, which means one of the tasks that C1 would be doing may be waiting for user input, right? One of the tasks that C2 is doing may be bringing or sending memory address to the RAM, right? Because there's a lot of things going on. Like for us, it's just adding, subtracting, like that. But at the hardware level, there's a lot of things going on, right? Like sending a memory address to the RAM, bringing the data into the register or the RAM, and then sending it to the register, right? Sending it to the process. After the processing, taking it back to the register. All these are instructions or executions done in the process, right? Overall, what we see is addition, right? At the user level, it's like addition, subtraction, multiplication. But there are a lot of steps going on inside, and these steps will be distributed among these cores, right? The reason is they don't like to keep any core idle at any time, right? So if this core is busy, it will quickly send the rest of the work to another core which is available, and then maybe come back to this later on. So that's called time sharing. It shares the CPU time, core time among these processes. Okay, right.
Yes, sir. Understood.
In multi-agent, we are talking about agents. Agents are, more powerful computer systems. Right, these are not just laptops or PCs, right? These are like mainframe computers or supercomputers, right? And obviously, you can imagine like their processing power, their capabilities are really high. And these are also distributed systems, but these systems can be distributed among large locations, maybe several countries, right? They are processed by several processes, not just one processor. These systems may have several processes, multi-processor environments, right? And in this, right, separate tasks or algorithms are processed by different systems. Earlier, what we saw was there was one program involved separate, a lot of processes, and these processes were distributed among the cores. But here, major tasks, right, are spread across powerful computer systems around the world. One big example is you have heard about big data for ICT. I'm not really sure whether you have done it yet.
Yes, sir.
You did, right? Yes, that's right. So big data processing is an example where multi-agent systems are used, because they cannot be handled by a small microcomputer. And each agent acts independently. Now, same thing happens in core. Core is also acting independently. They can execute their instructions on their own. But here, independently means without any user's intervention. Automatically, right? And thus we call them autonomous. Why are they autonomous? Because they use AI, artificial intelligence, right? They know what to do with the data. We don't need to give instructions step by step, right? Because they are already programmed, pre-programmed, and also they make judgments, reasoning, comparisons, and they take their own decisions based on a knowledge base that we have given. And also these agents can talk to each other because they use AI. They can talk to each other. Just imagine, like, again, coming back to that school project where your friends are working on. Each student can be taken as an agent because they have their own thinking, own logical reasoning, right? And then you talk to each other, you come up with decisions, agreements, right? Something like that. And then you work on your own, right, to accomplish certain tasks. So they do negotiations, coordination, right? It involves artificial intelligence, right? So the best example that you can take here is big data processing, right? In big data, some of the characteristics in big data processing is we are dealing with large volumes of data, large volume, usually measured in petabytes of data. And these data are coming from a variety of sources, various sources. Right now, these sources are normally in a database. Of course, the source would be a paper-based, form or something, right? But here, the source can be a blog, a website, a social network, right? Sensors, mobile devices, right? You go and like a post in a social network, that is also data for big data processing. So it comes from a variety of sources, right? And then it uses artificial intelligence, and it is used to predict a future outcome, right? So this kind of processing has to be done in a multi-agent system. Okay, understand?
Understood, sir.
Okay, then we come to the von Neumann architecture. Now we saw that later only the memory was added to the computer system, right? Before that, everything had to be fed from outside, one after the other, including data and instructions. But von Neumann came up with an architecture that revolutionized the computer systems, because this is still in use, right? Modern day computers are also based on this von Neumann architecture. What happened? He brought this in 1945. His computer architecture design consists of a CPU, right? Central processing unit, right? Which consists of three parts. What are the three parts? You have the control unit, you have the ALU, and you have what is known as registers. And these three, of course, you know already. You have learned this in smaller grades as well. CPU is divided into three parts: control unit, ALU, and registers. Okay. Salman, are you having a problem with the connection? Okay. Right. So the input output is already there. Right. And the new addition was this memory unit. Now, as you can see here, the memory is having a double-headed arrow towards the CPU, right? Now, earlier here, we talked about storage, but we talked about two examples: primary memory and secondary storage. Okay, but in this case, in this diagram, remember, you can see this unit is directly communicating with the CPU. Directly communicating with the CPU. So you have to be very careful, right? They give a diagram like this. You need to look at the arrowheads and the components. You can see it is directly communicating with the central processing unit, which means this is RAM. Okay, so this memory unit is referring to RAM. Why? RAM is the working memory. This is the working memory. This is where we work. This is where right now you are listening to me. I am teaching. We all work in RAM. So RAM is the one which is supplying all the data and instructions to the CPU. Right. In this diagram, this was connected to process, right? So this is an overall diagram, right? So here this storage can be primary memory or secondary storage, right? But when it comes to von Neumann architecture, it has to be more detailed. That's why you get these all these components, right? So in the exam, if they give this diagram or a similar diagram and ask you to identify this, don't write.
So for the exam, should you remember all the registers that you have shown here?
No, this is of course I took from internet, but just knowing one or two registers would be enough, right? In the book, of course, I think they have given. Wait a minute.
So could you upload the presentation to the group?
Yeah, of course. I will. Right.
Okay, sir, thank you.
Okay, wait a minute. I think they have given. Yeah, they have given three: accumulator, program counter, and CIR. And those three are here, right? Accumulator, program counter, CIR are there. Except that two more are listed here. Okay. So if they give a similar diagram, this can't be storage. Okay, I mean this can't be secondary storage. Why? How do you design? Because it directly communicates with the CPU. In CPU also you can see it's the register. Okay, and if they have given like these three rectangles blank and asking you to identify them, this has to be this rectangle has to be registers, not ALU, not control unit. Why? Because you can see that if this is RAM, right, RAM has to communicate with registers. Okay, you should know what registers are, right? Registers are the memory locations inside the CPU. It's the memory inside the CPU. Okay, It's the fastest memory in the computer. Registers are the fastest memory in the computer. Okay, it's faster than the RAM. It's faster than the cache. Okay, so this has to be the register, because the RAM is communicating directly with the register, and the data and instructions are going in and out. And these two can be changed, no problem. Right? This can be controlled arithmetically or vice versa, doesn't matter. But remember, this has to be registers because it's directly communicating with the RAM. Okay, so be careful when you get a von Neumann diagram like this or a similar one, right? Because there can be so many similar diagrams. Okay, von Neumann architecture is based on the stored program computer concept. Okay, so this guy came up with an idea of a stored program. As the name says, stored program is the program is stored. Where is it stored? It's stored in the RAM, right? But before RAM, it's stored in the hard drive. Okay, that's what we do, right? We run, we write a Python program, and what do we do first? We store it here in the hard drive. And then when we run, what happens? From the hard drive, it is taken into the RAM. And from the RAM only, it will send the data and instructions to the CPU. CPU where? Registers. Because even the brain has to store the data and instructions at least for some time before it is being processed. When I ask you to add 2 and 3, what would you do? Don't you feel that it's kept in a certain memory in your brain, and just before you add and soon after adding, don't you feel that it involves some kind of very fast memory in your brain, right? And also you can recall things that you learned previously because you have a memory similar to hard drive, a permanent memory. So our brain also has all these types of memories. Okay, we have the hard disk, right, or the permanent storage, secondary storage. We have the RAM, right? Because right now you are listening to what I say, so you are using your RAM. Okay, just the moment you process, and soon after processing, you feel like there's a very fast memory involved in your brain. That is registers. Okay, so we also have the same concept. Only thing is we are not efficient. We mix all our memories, but this guy is so efficient, right? So the stored program concept brought by von Neumann is where the program is brought from the hard drive to the RAM, and from the RAM it is supplied to the register. So now, after this concept, programmers could write a program, store it in the secondary storage, and run it anytime they wanted. So the whole computer system was changed. Why? Because before the stored program concept, they had to feed the data and instructions separately from outside, right? Because the computer couldn't store that program. So then and there, when you're running the program, you had to feed everything, right? By changing the wiring system, because those computers didn't have keyboards, didn't have other forms of input, right? We are talking about the time during the World War, or after World War, soon after World War, even during the World War, right? So that is known as stored program concept, where the programs could be stored, written and stored in the hard drive, brought them to RAM when they are being run, and the RAM is responsible for feeding the data and instructions to the registers, right? And registers kept those data and instructions before they are being processed by the ALU, right? In fact, it is right to say that ALU is the computer, because that's where all the calculations, logical and arithmetic operations are carried out. So in the whole computer system, we can take ALU and call it the computer. That's correct, because that's where everything happens. That's the brain, even though we call the CPU the brain. Okay, understood?
Yes, sir.
Right. Now, the other thing you have to remember here is when where instructions, instruction data and program data are stored in the same memory. That means you keep, right? You keep data and instructions both in the same RAM. The RAM will hold both the data and instructions, same memory, because everything runs on the memory. Right now, the operating system runs on the memory RAM. This presentation runs on the RAM. The drawing that I do runs on the RAM. Everything, data and instruction both. But before the stored program concept, these data and instruction had to be fed separately. And now, because of his stored program concept, von Neumann architecture, we could store both of them in the same memory, which is the RAM. Right. So, in short, von Neumann architecture, John von Neumann, a computer scientist, wrote a concept called, an architecture called von Neumann architecture. Before von Neumann architecture, data and instructions had to be fed from outside separately. Because von Neumann architecture, a memory came into the system. That memory is the RAM, right? Then the CPU was divided into three parts: control unit, arithmetic unit, and registers. It was the registers which was the fastest memory in the computer, and the registers directly communicated with the RAM. So the RAM was supplying the data and instructions both to the register, and the RAM could store data and instructions together. So data and instructions were residing in the same memory. And the programs could be stored permanently using the secondary storage devices like the hard disk drive. And those programs were brought into the RAM when they were running, and the RAM supplied the data instructions to the register. Right now, you have heard about something called cache, right? In ICT, you learned about cache,
Yes,
right?
sir.
Yeah. Okay.
It's
Where
stored
does?
for,
Yeah.
yeah, it's stored for data. It stores data, no, temporarily.
It stores data and instructions that are used regularly and recently stored. Recently used data and instructions are stored in another memory called cache. Now, why did they bring cache? Now, actually, cache was introduced later on, right? Way back. Way after this stored program concept and the von Neumann architecture. Why did they come up with the memory called cache? Because compared to RAM, registers were really fast. Now we have two memories with considerably different speeds. Register is very fast, extremely fast. RAM is quite slow compared to register. So there was a bottleneck later on when the tasks were much more complex, right? There was a bottleneck. Register is waiting, RAM is trying to supply fast but can't, but the register is too fast and it had to wait. So there was a bottleneck, right? So the performance went down. So what they did was they came up with another memory called cache, C-A-C-H-E, cache, right? And they put it in between the registers and RAM, right? Why did I draw it like half, as a half rectangle here? Because the data and instructions sent from the RAM to the register, right? Not all data and instructions sent from the RAM to the registers are stored in cache, right? Cache will store only the frequently and recently used data and instructions, right? That's what is it? I mean, we use cache in browser, we use cache in apps, right? And we do something called we clear the cache, right? So that, why do we do that? Because it stores all the recently and frequently used data. So when we clear the cache, it is ready to accept new data, fresh data from the RAM. So only some of the data and instructions will go through the cache from the RAM. Okay, and the cache will supply it to the register. Okay, now if so this cache concept solve the bottleneck issue. Otherwise, the registers had to take it only from the RAM. Okay, but remember, most of the data will go directly from the RAM to the register, right? Only a certain amount, right, where the data are used frequently and recently are kept in cache. So this will make the overall process fast because you don't need to communicate with the RAM all the time. You can take some from cache as well. And cache is very expensive. That's why it's small. Usually you get like 8 MB, 4 MB cache, right? And more cache means more expensive. And actually, in fact, all these three types of memories are very expensive because they're fast. And increasing these memories will definitely increase the price of the computer as well, right? Okay. So remember, Von Neumann didn't introduce cache, okay? That is some extra information, but in his design, control unit, ALU, registers, input devices, output devices, and RAM, right? Secondary storage was actually there at that time, like it was only magnetic tapes, and every time they had to put the tape and read it, but it was serial access, not fast at all. But with this design, we had the hard disk drives and other permanent storage, fast storage units. Okay, so the CPU is it's also called the microprocessor or the processor, right? Now you learned about the control unit and ALU. What is the job of them, right? So the control unit is responsible for coordinating. Okay, before that, ALU is responsible for performing arithmetic and logical operations, right? Arithmetic operations are the addition, subtraction, multiplication. Logical operations are and or not operations. And controlling, and also the data and instructions have to come from the unit input devices. They should be passed on to output devices, right? And then they should be read from the RAM to the register to the RAM, right? And this whole process is coordinated by control unit. So this does the coordination, right? Coordination of tasks related to the von Neumann architecture or the stored program concept, right? ALU carries out the arithmetic and logical units, and the purpose of register is to store data and instructions before and after processing, right? This will store data and instructions before and after process. Now, registers is a beautiful concept because they don't just have one memory call register. In fact, it is divided into several parts, right? For different tasks, they have different registers. So in the book, they introduce a accumulator, program counter, and current instruction register. Okay, what these do, right? You get the accumulator, and as the name says, accumulator, accumulate means collecting, right? Accumulator, where the intermediate arithmetic and logic results are stored. That means this job of this is to store the data and instructions before they are being processed by the ALU, before and after, right? Accumulator. So when the data is read from the RAM, it will be held in the accumulator, and then it will be taken to the arithmetic unit from the accumulator, and then after processing, there will be the accumulator, right? Intermediate arithmetic and logic results are stored. Stores data before and after execution by the ALU. Program counter contains the address of the next instruction to be executed, right? Now you hold the data in the accumulator, and you should know what to do with that, right? So you need instructions. So the program counter will contain the address. Why is it the address? Because we need to bring the instruction also from the RAM, and RAM has memory locations, and these memory locations have addresses, right? You have to address, you have to find out where these instructions are stored in the RAM using the address. Imagine RAM is like a Excel sheet, right? And in those cells, you have stored data and instructions, because I told you both data and instructions are residing in the same RAM. So in order to bring a data item or an instruction from that Excel sheet, you need to refer to them using the cell address, right? So here we talk about the memory address, right? So program counter will store the address of the next instruction that we are going to bring from the RAM, okay, to be executed. Then you have the current instruction register, contains the current instruction during the process. So the instructions are executed one after the other, right? And CIR will hold the instruction that is being executed right now, right? Contains the current instruction. That means the instruction is already brought into the register. But program counter will have the address of the next instruction, right? And then that address will be sent to the RAM to pick the instruction and bring it and put it into the current instruction register when it is being executed. Okay, so once again, accumulator, as the name says, will collect the data before and after processing by the ALU. It's like a temporary location to keep them in between, right? Immediately. Just a minute. Right. And program counter will hold the address, the memory address of the next instruction. And the CIR, current instruction register, will hold the instruction that is being used right now. Okay, just remember these three, and additionally MAR and MDR. What MAR does is holds the memory location of the data that needs to be accessed. Memory location of data. You need to bring data from the RAM. For that also you need an address, right? Just like that Excel sheet. So this will contain the address of the data that needs to be accessed from the RAM. Address, okay? Then memory data register holds the data that is being transferred to and from memory. So this will keep the address of the data location, and this will hold the data that you brought from the RAM. Okay, so remember the use of addresses here, right? Whether you are bringing a data item or an instruction from the RAM, you need an address because you need to find it in the memory, right? So MAR will hold the memory address of the data. MDR, memory data register, will hold the data item that is brought from the RAM. Accumulator will hold the data just before and after processing by the ALU. Program counter will hold the memory address of the next instruction to be executed so that it can be brought from the RAM. Current instruction register will hold the instruction that is being processed right now. Okay, is that clear? Is that clear?
Sir, yes, sir.
Let's move to the last 2 slides in this section. Control unit. Okay, we talked about the control unit, and I told you that this is coordinating the whole set of tasks. You can think of this as a traffic police who is coordinating the flow of traffic, right? The control unit controls the operation of the computer's ALU, memory, input-output devices, everything, right? Telling them how to respond to the program instructions it has just read and interpreted from the memory unit. The control unit also provides timing and control signals required by the other components, right? This not only coordinates, this will also send. Actually, the coordination is done by means of sending control signals like orders, right? Something like, okay, ALU, start doing the calculation now, right? Okay, let's say something like, okay, RAM, get ready to send me the data, something like that. Okay, input device, keyboard, send the data, right? Send this data to the output device. The whole thing is coordinated, right? So one example of control signals that this sends is, this will send the, this will send control signals, or this will instruct the ALU to carry out arithmetic and logical operations. Okay, that's one example of control signals that this will send. Okay, right. Now, even though the control unit is there, you have heard about something called an internal clock. An internal clock. Have you heard about the internal clock? For ICT, you have learned that. Internal clock, there is an internal clock in the CPU that gives pulses. Remember?
So, no, so we haven't learned that for ICT.
Why in the memory and process chapter is there no?
So, impulse, not sure, sir.
No, not sure. You have learned about something called clock speed.
That is, that I heard.
Yeah, that's the clock. Okay, that's the internal clock. Okay, right. Now, even for the control unit to send control signals, it can't does it on its own. There should be something to synchronize this whole thing, something to like, it's like let's say for you to work, your brain should give signals. Okay, now wake up, now attend this class, right? Now you ask for the link. Now you check the link whether the previous link is working. So all these were instructions carried out, right, in your brain, right? So there, don't you feel that there's something which synchronize these instructions, like which will give a kind of a go, kind of a pulse to start those instructions. So here also, for the control unit to generate control signals, right, there is something called a clock, an internal clock, right? So in this architecture, if they have given a rectangle that is connected to the control unit, right, it has to be the clock. Okay, or let's say these two rectangles are blank, but you see another rectangle joined to the control unit, I mean the top rectangle, right? Then this can't be ALU, this has to be control unit, right? Because there is something which gives pulses, which generate pulses for the control unit to does its operations, to send control signals, right? It's like the traffic police is there, but there will be another senior traffic police officer, right, who is coordinating those traffic guys. Always in a junction, have you seen? There's a big guy who is controlling, who is coordinating the small guys who are controlling the traffic. So something like that, right? So here the big guy is clock. So if they have drawn a line and line connecting this box to one of these, this has to be, I mean, if it is this one, this has to be the control unit, not the ALU, and this can be the ALU. So be careful when you are selecting control unit and arithmetic and logic unit. Check whether they have drawn a clock unit as well. So the purpose of clock is to generate pulses. Generate pulses like tick, 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 like that. Right? How many pulses generated is known as clock speed. Right? Okay, I'll write that here. Right? You have learned about clock speed. This is the number of pulses generated by the internal clock in 1 second, right? And this is what is written popularly as gigahertz, right? Like 2.6 gigahertz. If it is 2.6 gigahertz, that means this clock will generate 2.6 billion pulses in 1 second. Right? So it generates 2.6 billion pulses in 1 second. Right? So if you have 4 cores, and if each core is running at 2.6 gigahertz, right? Now you can imagine the overall speed, right? Each core will generate, each core, remember, each core has a clock. Each core has a clock, and each clock will generate 2.6 billion pulses per second. And for these pulses only, instructions are carried out. Because for these pulses only, the control unit works. Control unit works means the whole processing takes place. Okay, so more pulses generated, more processing can be done. That's why it's going to be fast, right? So remember, 2.6, okay, clock speed is not the number of instructions. That's one of the misconceptions that we have, right? It is taught nicely in the ICT book. Clock speed is not the number of instructions carried out. It is the number of pulses generated, clock ticks generated. For these ticks only, the process will work, right? So if the number of clock pulses are high, obviously the process is going to execute more instructions. It's something like this. Just remember like this. If you work, you don't like to work, you are lazy, you work only if your parents scold, right? Just an example, right? More they scold, more you work, right? Which can happen the other way also, right? More they scold, least you work. That can also happen, but just imagine like, okay, more they scold, you work. It's something like that, right? More clock pulses generated, more processing will take place because the control unit is going to act fast for these pulses, right? Which means it's going to coordinate this whole task of reading data and instructions on the RAM, executing them using the ALU. So the whole processing takes place like that. Okay, so clock speed and clock pulses. Okay, now the other thing is this. Now you learned about a lot of components here, right? ALU, CU, registers. Registers also had different types of registers. Then RAM, cache. Right? What about the data and instructions sent among these components? That is also very important, right? You have to send this data and instructions here and there between these internal parts, among these internal parts. And that will also have a major effect on the performance. Now that's where we talk about buses, right? You may have already heard about the concept of bus speed. You must have heard about bus speed, bus width, right? So bus is responsible for transferring data and instruction among these components. Okay, so bus is actually a collection of parallel lines, right? Collection of parallel lines, right? You know, if you have parallel lines like this, right? And remember, each line can send either 1 or 0 at a time, a bit, 1 bit at a time. So if you have 1, 2, 3, 4, 5, let's say 6, 7, 8, right? 8 parallel lines, you can send 8 bits at once, right? So the number of parallel lines, right, will depend on and will affect the amount of data that we send at once, right? And that is called I mean the number of parallel lines we have is called the bus width. Now this is similar to the lanes on road. When you have more lanes, more parallel lanes, more vehicles can move, right? More data can move. So similarly here, when the bus width is more, you can send more data. So this is another thing that you should be aware of when you're buying computers, the bus width. And bus width is measured in bits, right? Not just the bus width is not enough, right? Even though we have many lanes on the road, right? Vehicles also have to pass fast, right? They also should move fast. Just because we have, now for example, you know, we have the what, the highway, right? In the highway, some vehicles move at 100, some move at 20 kilometers per hour, right? Something like that. Just because we have parallel lines, is not going to be fast, right? The data should be moving fast. So that is called the bus speed, right? That is also something you should look at when you're buying a computer, bus speed. And bus speed is measured using megahertz. Bus width is measured using bits. So you should look for a computer which has a higher bus width and a higher bus speed. Okay, these are some of the technical specifications that you should look at, because this is why people say like, okay, I bought a very fast computer, all right, a good brand, but after some time I noticed that this is lagging and this performance has gone down. The reason is these internal specifications are not matching, bottlenecks are there, right? So buses are the means by which data is transmitted from one part to another, connecting all major internal components to the CPU and memory. A standard CPU system bus is comprised of control bus, data bus, and address bus. Now there are types of buses. Just like on the road, there are lanes for buses. I mean, buses, right? And then there is a lane for light vehicles. There's a lane for bicycles. There's a lane for pedestrians. Likewise, there are different channels. Just like that, here we have different buses. Address bus, what does it do? It transfers the addresses, memory addresses. Right now, earlier you saw MAR, right? Memory holds the memory location of the data that needs to be accessed. So this address in the MAR will be transferred using the address bus. Right? See how organized the computer system is. Right? For every task, there's a separate component. Right? Data bus carries out data between the processor and memory and input output. So all the data are sent through the data bus. And the control signals sent by the control unit is transferred to the control bus, carries out the control signals, commands. Control signals are actually commands, okay? Orders. That's why it's called, it's taken as, it's, you know, as an example, we take traffic police, gives the orders. In order to control and coordinate all the activities within the computer, control bus. So addresses, data, control signals are sent through different buses, different channels, parallel lines. Addresses using address bus, data using data bus, control signals in control bus. Is that clear? Is that
Yes,
clear?
sir.
All right, finally, coming back to memory. Memory consists of RAM, mainly RAM, but you know, we also have something called ROM. We'll talk about ROM tomorrow. And this is also called primary memory and main memory. And this is really fast. It's faster than the secondary storage, right? And it is the memory which is directly accessible by the CPU. CPU doesn't access the secondary storage directly. It's the RAM which will access the secondary storage. Okay. RAM is split into partitions. Each partition has an address and contents, right? But you know, now you understand that RAM holds the data and instructions both are kept in the same memory. The address will uniquely identify every location in the memory, whether it is RAM, whether it is register, whether it is hard drive. You need to have addresses for memory locations. Otherwise, we won't be able to access what's in there, right? Loading data from permanent memory, hard drive, into a fast and directly accessible temporary memory, RAM, allows the CPU to operate much quicker. Imagine that RAM wasn't there. If RAM wasn't there, the computer will be extremely slow, right? Will be extremely slow because there's a huge difference between the registers and the hard drive. So what they did was they brought this RAM concept, and still the RAM was not enough, right? So they brought cache into that, in between RAM and registers. So that's how the modern computer is built now, right? The modern computer has RAM, has cache, has a large bus width and a higher bus speed, and also the CPU is divided into cores, multi-cores, physical cores and logical cores, right? Always it's better to have a higher number of physical cores, then your logical cores will increase. Logical core is a virtual concept, right? When a physical core can work on multiple instructions at the same time by switching really fast, virtually there will be like 2 cores. So normally what they say is if your CPU is having a certain number of physical cores, just double the value, you get the number of logical cores. So if there are 4 physical cores, you will have 8 logical cores, right? But what is more important is the physical core, because physical core is a hardware component, hardware processor. Logical core is a virtual concept. Okay, right. So that's the end of today's lesson. We talked about these models, computational models, the importance of storage, then the von Neumann architecture, right? And the components in von Neumann and what their jobs are. And then we talked about buses, and we talked about types of registers, the purpose of the control unit, and the importance of RAM as well. Okay, right. So I'll see you tomorrow. When is your computer science paper?
Sir, we're having tomorrow, day after, sir. I think day after.
Day after computer science? No, day after you have ICT.
And also Wednesday.
No, the computer science only.
Yeah, you have got the timetable messed up.
So we have it on
Really?
Wednesdays, I think, computer science.
Yeah, maybe Wednesday.
Wait, let me check. Yeah, ICT. Yes, ICT.
ICT is tomorrow, practicals, yeah.
Yeah, day after.
Day after.
Sorry, not tomorrow,
Sir,
day
they're
after,
having
day
it on
after.
Friday, sir.
Friday. Computer science Friday.
Yes, sir,
Friday.
paper 1.
Good
Paper
luck.
1. Okay. So in between, Friday computer science paper. No? So we'll try to meet on Thursday to do some paper questions. Right. You know, this happened because of all these events in school. So what to do, right? Time. We were struggling with the time, so but luckily I think they have kind of reduced the content that will be tested. Otherwise we were supposed to finish the hardware and software, the whole chapter, which is impossible. According to the scheme of work, we had to finish both, and you see now. Right, so don't miss, right? I have recorded and I'll upload. If you miss, go through that. And also don't wait until we do paper questions. You can do it now itself. Just go to the
Sir. So
Yes,
you'll upload papers, right?
Okay, I'll upload papers, a few papers now. Okay.
Okay, sir.
Right.
Okay, sir.
Then see you. Good night.
Okay. Thank you, sir.
Thank you,
Okay.
sir.
Enjoy the lesson.
Bye, sir.
Okay.
Have a good day.
Good day.
Have a nice day.